going into the actual code. Alright, so first up I've got this breadth first search. It's going to use a heap that I created, and it's going to take this first path and push it on there. Path is a class that I created to hold information about the game state and the states that came before it. With the breadth first search, getting the best optimal solution. It is kind of a brute force approach. It can be too complex. You've got the depth first, and so what this does, this is my successor function here. It's going to look in every direction to see if there's a move. If there's not a legal move, then it's going to continue. If it's gone somewhere that it's already been in that path, then it moves along as well. Otherwise, it's going to go ahead and put that new path either on the stack or heap or whichever search algorithm happens to be using. With it up first, it's performed very bad. It doesn't guarantee that it's going to get the best solution. It doesn't even guarantee that you will get a solution. Iterative deepening, it performed a lot better than the depth first, but not quite as good as the breadth first. In here, and then while we're within our depth limit, it's going to make this stack, and it's going to call this other function here, which is going to have our successors in it. With that, what it does is it returns the shallowest solution. For this particular application, it doesn't necessarily mean that you're going to get the best solution just because it's the shallowest. Alright, next up we've got our uniform cost. With this one, it's going to be the first one here that uses our g of n, which is going to consider the cost of the path to the node of n. Variation on breadth first, but what it does is it only considers the cheapest path. So if it's already, so we've got this dictionary here to keep track of ones that we've already been to at that same value. So if it's already been there and it finds that this new one cost less, then it'll replace it with the new one and throw out the old one, and vice versa if this one costs more. Okay, so then there's the best first search. This is the first one that uses a heuristic. It wasn't a great heuristic because it just considered the number of pieces that were out of place. It does save us from using paths that are clearly not optimal, but that doesn't mean that it's going to guarantee an optimal solution. But it is an admissible heuristic. Then we have the first A star, and this one uses a combination of our G of n and then the H of n. This one wasn't, it was okay. It wasn't the best heuristic, but it did return results. A star 2 was better. With the A star 2, instead of using the heuristic that just counted the number of misplaced tiles, we used one that used the Manhattan distances to consider our relative moves. So that was a better heuristic and gave us a better result. I think it actually would have returned the hard one if it had been allowed to run long enough. This A star 3, which was the heuristic that I created, and what it does is it works a lot like the A star 2, but instead of using just the Manhattan distance, it goes ahead and weights those based on the cost of the movement. This way it returns the best possible cost, it performs the best in matters of like time and space, and it's also the most optimal. Here is my main where I have the boards set up and then all the solutions. But so here we can see the breadth first search on the easy board comes up real fast. Here it is on the medium. The hard does not run for breadth first. Right, next up we've got depth first. The solution on easy. Right, we've got our iterative deepening. uniform cost. A star. And I think I forgot to show that the uniform cost also returns on the hard state.